Welcome to my talk about constraining primordial features beyond the linear regime. I'm Benjamin Wallisch, a postdoc at the Institute for Advanced Study at the University of California, San Diego. In the following, I will present recent work in collaboration with Florian Beutler, Matteo Biaghetti, Daniel Green, and Andrzej Slozar on probing inflation using large-scale structure data. Before diving in, let me, however, take a step back and have a look at this picture of our universe. Using observations of light, we can directly observe the universe back to a time about 400,000 years after the Big Bang, when a cosmic microwave background was emitted. We can also use galaxies and other observables of the large-scale structure of the universe, in addition to the observations of the CMB, to measure the evolution of the universe since then. If we want to probe times before last scattering, for example, to investigate whether the early universe evolved as predicted by the standard models of particle physics and cosmology, or whether our universe underwent an inflationary epoch, we essentially rely on the observations at later times and finding imprints of these early times in these. Apart from Big Bang nucleosynthesis, we have been mostly relying on the CMB to do that. However, as I will show you, large-scale structure data can very much contribute to this discussion already today. As an example, I will discuss how measurements of the so-called BO spectrum of large-scale structure can constrain primordial feature models. In a somewhat larger scheme of things, I'm interested in expanding the science return of these late-time large-scale structure observations, in particular, given the vast amount of data that we will get in the next decade. So far, we, however, cannot use the full statistical power of these surveys, to some extent, due to the various nonlinearities. So my goal is to not only extract more information from these observations, but also to go beyond just constraining the background evolution of the universe and constrain the fluctuations around this background. To this end, I've now been able to learn about both neutrino and primordial perturbations using the BO spectrum, which I will introduce next. Well, okay. First, this is the well-known matter-power spectrum today, the Fourier transform of the two-point function of the matter perturbations, which has now been extracted from various kinds of observations. As I already mentioned, however, and is depicted by this dotted line, the linear matter-power spectrum undergoes various nonlinear processes in a late universe that have to be understood and modeled in order to reconstruct the linear perturbations. To circumvent some of these problems, we can decompose the spectrum into two parts: a broadband or no wiggle spectrum, P no wiggle, and a wiggle spectrum, P wiggle, which captures the Baryon acoustic oscillations that we also see in the CMB. And so this wiggle spectrum is indeed shown on the right on this slide. And I'm also referring to this as the spectrum of Baryon acoustic oscillations, or simply BO spectrum for short. Now, you might say that this is only part of the matter-power spectrum and hence contains less information. Yes, that is true. However, it is still sensitive to the early universe perturbations that we are after, is less affected by gravitational nonlinearities, and even more importantly, we know how to theoretically compute these remaining nonlinearities. In addition, this observable has now been robustly measured at high significance with the data being readily available, for example, from BOSS. This has previously allowed us to constrain the free-stream nature of neutrinos in the early universe, and has now allowed us to probe the primordial or inflation universe, which I will turn to now. It's well known that vanilla single-field slow-roll inflation leads to a power spectrum with an almost scale invariant power law, which can be parameterized by its amplitude and spectral index. At the same time, we can also attempt to reconstruct the inflationary power spectrum over the range of scales that the CMB is sensitive to. The result of such reconstruction on Planck data is indeed shown in the figure on this slide. And we see that it's constrained to be a power law with a small spectral index. However, quite a number of inflation scenarios predict departures from this simple picture, and for instance, additional structure on top of this almost scale invariant power law. In fact, there's a rich thread of literature on quite a number of such possibilities, including sharp features, which usually originate from some new physics that's introduced at a certain time during inflation. Resonant features, for which the background doesn't follow, but oscillates around the attractor solution, or primordial standard clocks, for instance. In the following, we will focus on these simple phonological parameterizations of so-called linearly and logarithmically spaced features, which are closely related to the sharp and resonant models that I just talked about. This means that we are interested in sinusoidal oscillations around the power law power spectrum with either oscillations in K or log K, so kind of linear in wave number or logarithmically in wave number, as depicted in this figure on the right. Or equivalently, you can also look at this figure, which shows the entire primordial power spectrum with just the power law or the additional oscillatory features. As I previously said, these features have been searched for extensively in the CMB, but how do they look like in large-scale structure, or in other words, in the meta power spectrum or the two-point correlation function? Well, this is exactly what's shown here on this slide for linear and logarithmic features in blue and red, respectively. That will actually also be the color coding for the rest of this presentation. In Fourier space, in the top row, we see the additional oscillations, as one might assume, given the simple transfer of power in linear theory. In real space, on the other hand, we see a second peak at the physical distance given by the feature or frequency for linear oscillations, as I might also expect given their physical origin during inflation. The logarithmic oscillations in Fourier space, on the other hand, translate into additional wiggles in real space, given that no physical scale is attached to them. Let's now finally come back to the BO spectrum and the respective signature of our features. Since the power law spectrum is part of the broadband, the features simply appear as oscillations on top of the Baryon acoustic oscillations. So this is the signal that you want to go after. At the same time, this also means that we don't lose anything by discarding the broadband spectrum in the search for these primordial features. However, we still have to be careful with nonlinearities, as I mentioned, when we consider large-scale structural observables. So in order to introduce those, let's first look at the well-known case of the impact of gravitational nonlinearities for the standard BEO. On the one hand, nonlinearities arising on small scales around or beyond the nonlinear scale are not important in this case, because the BO scale, which is about 150 megaparsec, is much larger than the nonlinear scale of a few tens of megaparsec. However, at the same time, the BO peak is actually damped, and that's due to large-scale bulk flows in the universe, which do have to be taken into account when comparing theory and data. So let's now go back to the possibly imprinted primordial features and consider these types of gravitational linearities. First, let's again look at those small-scale linearities. For linear features, the argument is very straightforward, given that they are approximately of the same form as the Baryon-acoustic oscillations, and we know that the BO with a frequency of 150 megaparsec and its phase are effectively unaffected. So a closer but kind of conservative analysis then shows that we don't have to worry about small-scale linearities for linear features, provided that they have large enough frequency, say about 80 megaparsec. For logarithmic features, it's not quite as straightforward, given that their frequency is not a fixed physical scale. However, in this case, the limited sensitivity of our observations actually helps us, because BOSS and most of the future experiments only have a sizable signal-to-noise over a limited range of scales. This means we can decompose the logarithmic oscillations into a basis of linear features and then apply the argument for linear features. In this way, we can then also estimate a conservative lower bound on the logarithmic feature frequency so that they remain unaffected. So we don't have to worry about small-scale linearities, provided that we apply these frequency cuts. So what about the large-scale bulk flows? In the standard BO case, these bulk flows, which are depicted in the bottom left plot, lead to a distortion of the primordial linear overdensities, as is shown when going from the top left to the top right figure. Now, the same will, of course, happen to the feature signal, given that we saw this second peak in the correlation function for linear features. However, since the functional form is still the same, we can again repurpose the standard calculation to compute the effect of these bulk flows for these linear features. For logarithmic features, it's again somewhat more complicated, and the intuitive picture underlying this calculation does break down. However, the underlying mathematics still works and goes through. So as a result of this further calculation, we can draw the conclusion that the primordial features are exponentially damped in a similar way as the standard BO signal. This then results in the conclusion that the primordial features are exponentially damped in a similar way as the standard BO signal. And in particular, we do have to take this effect into account in any possible data analysis, as is indicated in this plot, in which the linear prediction is shown with dashed lines and the nonlinear spectrum with solid lines for some fiducial damping scale. If it didn't take this effect into account, we would completely overpredict our constraining power. So this is what we are finally turning to now. After having established the large-scale structure theory related to these possible inflationary signals, we wanted to analyze the current BOSS data. While some basic forecasts had been performed for future experiments, nobody had considered BOSS, and especially its existing data yet. So we performed a large suite of likelihood-based forecasts, not only to estimate the sensitivity that we could expect, but also to especially establish the analysis itself and provide for kind of useful cross-checks in the analysis. And then after having validated our new feature search pipeline in these forecasts and our mock catalogs, we then turn to the BOSS DR12 dataset, which is a dataset that's based on the spectra of about 1.2 million galaxies, which were observed between redshifts of about 0.2 and 0.75 over roughly a quarter of the sky. And so in total, we then fitted 23 parameters to the BO spectra of these two redshift bins, which simply meant to extend the standard BO analysis, which uses 10 parameters per bin, by 3 additional primordial feature parameters with the given feature frequency ranges, with the lower bounds given by a conservative requirement of not being affected by small-scale nonlinearities, and the upper bounds being dictated by the survey volume or window function of BOSS. So in this way, we obtained these constraints on the overall feature amplitudes for linear and logarithmic features on the left and right respectively. And hence, the first constraints on these inflation models from large-scale structure. We in particular see here that the current BOSS data is able to limit these amplitudes to about 1% relative to the primordial amplitude, which is, I think, rather impressive. In fact, however, it becomes even more impressive when we compare these results with the current constraints from Planck, which are shown here. Our new constraints are not only competitive, but the BOSS limits actually improve over those from the CMB, except at small frequencies, which is partly related to a large degeneracy with the standard BO signal in large-scale structure. And so finally, we can not only compare, but also combine these constraints and obtain these 95% upper limits that's shown on this slide, which are, of course, dominated by BOSS in this kind of given frequency range, except at the small scales. While this seems already pretty impressive, let me have a look into the future before wrapping up. Our forecast shown here indeed suggests that the future is very bright for constraining these inflation models using large-scale structure surveys, with the potential of improving the constraints by at least 1, if not several orders of magnitude. And it gets even more impressive if you compare the reach of these surveys with CMB measurements, which don't have such a reach in overall sensitivity, but will always dominate, admittedly, the range and frequency, simply because we can't beat the cosmic volume back to the last scattering surface with a galaxy or 21 centimeter survey. So to conclude, I hope that I convinced you that the BO spectrum is an interesting observable for the early universe, and that we can reliably perform primordial feature searches in this observable, which marks the first application of the BO signal to primordial physics. In this way, we were able to obtain constraints on these inflation models, which are already competitive over the given frequency range with those from Planck, and have a bright future with upcoming surveys. In the final take-home message, I would argue that with this analysis, we have now come to a point where we can say that not only the CMB, but also the large-scale structure of the universe point towards almost scale invariant and Gaussian primordial fluctuations. With that, I thank you for watching this video, and I'm looking forward to discussing it with you.